D.1, Introduction to Quicksort. Why we want to learn another sort. We have learned selection sort, bubble sort, insertion sort, merge sort. So now Quicksort. All right, yeah. Next, heap sort. Yeah. All right, yeah. Why? Yeah, first, this time, because for different sorts, we based on their different properties. So, because each one has its own properties, yeah. So we want to use those properties for different situation. Here, this time we want to emphasize overall performance. That's important. Because in our real world applications, we want to pick a good one with best overall performance. Yeah. So this new one, we focus on that overall performance. But in your algorithm design, actually it's very hard to, so although you try your best, try to get the best overall performance, but when you design, it's very hard to control that overall performance. How do you control that, right? Yeah. For this algorithm, after we compare all the sorts on the market, yeah, we do a lot of experiments, right? And at the end, then we, based on our experiment data, so this one has the best overall performance. Okay, yeah. So by the experiments, yeah. All right, yeah. So in the design, it's hard to control. Yeah. So nobody can control. Okay, yeah. Overall performance. Yeah. Yeah. So the same old problem number 4. Yeah. So we do it again. This time also divide and conquer. Yeah. So when we do divide and conquer, our focus could be different. Yeah. So here, let's compare with the merge sort. Merge sort, we also do divide and conquer. Yeah. But for the merge sort, our focus is different. We try to balance the data distribution. That's our main concern. Yeah. Balance the data distribution. Here, we do not go that direction. Okay. Yeah. So here we go a different direction. Yeah. Because we want to get a, different sort. So we have to take a different approach. Yeah. So let's look at the design consideration. Yeah. Goal, make the overall performance as fast as possible. Although that's our goal, yeah. In our design, we just try a different way. And then later we want to see if we can get the best overall efficient algorithm. Yeah. All right. But we can tolerate poor, worse performance. Yeah. Because you have to sacrifice somewhere, right? When you get a gain in some important place, but you have to sacrifice a little bit as some relatively minor aspect, yeah, because it's something like trade-off, yeah. So you cannot get the best result in all aspects, yeah, yeah. All right. More specifically, yeah. So we can, look at the divide and conquer. There are 3 steps in divide and conquer. So we want to see in each step, so what is the trade-off? We need to look at, okay, yeah. Yeah. Although we allow we accept some poor worst case performance. But the good thing is the probability for the worst case is very small. The probability is small. Okay? So you have a bottleneck. Yeah. So the worst case, the algorithm performs very poor. What do you mean poor here, right? What do you mean poor here? Poor means if efficiency is big theta of n squared. That's poor. Okay? Yeah. N squared. That's poor. Yeah. All right. But the probability is very small. Yeah. Then, when you take the average, so then that the impact of the poor worst case is very little. Okay? Yeah. So we don't worry about that. Yeah. Very little impact, very small. Yeah. All right. This time we want to change view on divide and conquer. Yeah. Yeah. So let's do the comparison with the merge sort. Yeah. Let's recall the merge sort. How did we do divide and conquer for the merge sort? Yeah. Yeah. So here I do a chart. Okay, yeah, 3 steps. Divide and conquer has 3 steps. First step, divide step, then conquer, then combine. 3 steps. Yeah. For the merge sort, divide, very easy, because you split your array in the middle. So you choose the point right in the middle. It's an easy split. You don't need to do a lot of work, right? Yeah. You just set the, boundary point for 2 subarrays. Yeah. So that is big theta of 1 computation cost. Yeah. Then conquer recursion. Yeah. So recursion, we just leave it. Automatic, recursive function calls. Yeah, so we just keep it, yeah, recursion. Yeah. Then combine step, merge, that's our merge operation. Yeah. Merge operation, best case, worst case. Yeah. Both best case, worst case, we have this big theta of k. Okay, yeah. Average case also big theta of k. Yeah. So that's the merge sort. Now, we want to change. We want to take a different way here in our algorithm design. Yeah. Trade-off, remember trade-off. Trade-off means divide step and a conquer step. You cannot do well at both sides. No, it's impossible to do well at both sides. Yeah. If in one of the 2 steps you do very well, then in the other step, then you need to do more work. You need to do more work. Yeah. Okay? Yeah. All right, so here we just want to take the opposite way. Opposite way. All right. We want to make the combine step very easy. Yeah, for this new idea, yeah. Combine step. So we want to make it, when we join 2 subarrays easily, we get a whole array ordered, sorted. Yeah, combine step very easy this time. Trade-off, okay? Yeah, but if you make the combine step very fast, then you have to do a lot of work at the divide step. Trade-off thing, okay? Yeah. Because sorting, you need to do sufficient amount of work, right? You need to do the total work. You need to do sufficient amount of work. You cannot, do the minimum work in all the steps, right? Then, when you add up, you do not do sufficient amount of work. Yeah. So when you save a lot of work in one of the steps, then you have to do more work in some other steps. Yeah. Yeah. That's the point. Yeah. So here, we save a lot of work at the combined step. That's our plan. All right. Yeah. Then we have to do more work at the divide step, big theta of k. Yeah. In this way, then our result algorithm will be different from the merge sort. No? Yeah, because, the approach is completely different. So we expect to get a completely different sort. Yeah. All right. Now, let's follow this idea. Try to fix all the details. Yeah. How to do it? Yeah. How do you make combined step trivial, right? Big theta of 1, that means trivial. Okay? Minimum work. Yeah. All right. Yeah. Yeah, so here, K means current data size. Yeah, because when we do recursion, every time the data size pass into the recursive function will be different. So it's a variable. Yeah, so that K, yeah, current array size. Yeah. All right. Yeah, so that new idea, so that will be our quicksort. Yeah. If we fix all the details, we will get the quicksort. Yeah. All right, so let's look at the combined step first. Yeah. We want to understand, how do you make the combined step so easy? Yeah. Yeah. All right, yeah. So let me use a diagram. So we will understand why we can combine two ordered arrays together, and we do not need to do much work. We get a whole ordered array easily. That's the situation we want to have. Okay? All right. That's our goal. Yeah. All right. Almost do nothing in the combined step. So that's what we want to have for this sort. Almost do nothing. Just join two ordered subarray, we get a whole ordered array. Yeah. So that is our, envision. All right? Yeah. All right. Draw diagram. First subarray, A subarray, and a B subarray. Yeah. Before the conquer step. Yeah. So we have a conquer step. Yeah. Before the conquer step. Yeah. These two subarrays are not ordered. Yeah. None of them is ordered. Yeah. In general. In a general situation. Yeah. Divide. So you divide. We do not expect any of the subarrays ordered. Yeah. All right? Yeah. No, yeah. But we have the conquer step, right? Yeah. Recursion, conquer, recursion. After we, do the recursion, at the end, each of the subarray is ordered. Yeah. Conquer step. Okay, all right, yeah. So then we need to combine, yeah. Combine these two ordered subarrays. All right. But we don't want to do a lot of work. So when we combine, so we put them together, and we want to do the minimum work, and we get the whole array ordered. Almost nothing. Almost nothing. Okay, minimum work. Put them together, the whole array is ordered. Is it possible? Yeah. Think about it. Is it possible? Yeah. Right. Yeah. Right. Yeah. Because in our merge sort, our merge step, we need to do a lot of work. Yeah. We need to do a lot of work, many comparisons. Yeah. So here we don't want to do. Yeah. So here we don't want to do any comparison. Okay. We don't want to do any comparison. We get the whole array automatically ordered. All right? Yeah, but in order to make that happen, you have to put certain condition on A subarray, B subarray. Yeah. The A subarray, B subarray, these two subarrays, they have to follow certain condition. Because in general, if you do not impose any condition in general, you won't have the property we need. Property we need. Okay? No costly merge step, almost do nothing. You won't have that property. Okay? Yeah. So some special condition we need to impose on our data after the divide step. No. No. All right, so we need to know that condition first. Before we move to the divide step, we need to know that condition first. Important condition. Okay? All right. After conquer whole, combine, do nothing. Yeah, that condition. Right? Yeah. So that condition is, this inequality. The value of any element in A subarray must be smaller or equal to the value of any element in B subarray. Or you can view in another way, the maximum of A subarray, must be smaller or equal to the minimum of B subarray. That condition. That's the critical condition we need when we do the divide step. If you don't have this condition, then so you won't get our goal. Okay, almost do nothing. No, you put them together. Because if you have this condition, think about when A subarray is ordered, B subarray is ordered, the last element in A ordered subarray is smaller or equal to the smallest element in B subarray, then you put them together, the whole array automatically ordered. Do nothing, right? No comparison is needed. Yeah. All right? Yeah. So after you get this point, then this condition we want to have at the divide step. Yeah. Because we need to do the divide step first, right? After divide step, then we do recursion, conquer, and after that, then combine. Yeah. Combine is the last step. Okay? So after divide, conquer, combine, then we get it. Okay? Yeah. All right. So this work, how to get it? How to get it? That's the challenging work we need to do, we need to solve this problem at the device step. Okay, yeah, all right, yeah. Now, our main focus, the most important step for the quicksort, device step. Yeah. Because combine step is trivial, right? You do nothing. You do nothing. You combine two ordered subarrays. Yeah. Then we need to do a lot of work at device step. Yeah. So next, we need to, address, we need to fix all the details in the device step. Yeah. All right. Requirement. When we do device step, you have to keep in mind your goal. You want to make sure when you split the given array somewhere in the middle, the two subarrays need to follow this inequality. That's not easy, right? That's not easy. How do you get that? Right? How do you get that? Yeah. So at this point, it's hard. Yeah. So we need to, when we understand, when we do analysis, so in algorithm design, we need to do a lot of analysis. Okay? In future, if you need to design certain algorithms, you really need to do a lot of analysis. Yeah. That's the hard work. Yeah. Here, let me show you the analysis part. Yeah. All right. Requirement, how to split the array into two subarrays, little a subarray and a little b subarray, such that inequality, a of I less than or equal to b of j. Yeah. All right. Yeah. Yeah. But at device step, we do not require a subarray is ordered, b subarray is ordered. No. In general, none of them is ordered in general. All right. So the ordering step, that part, leave the conquer step, right? After the conquer step, a subarray becomes ordered, b subarray becomes ordered. Recursion, conquer step. Yeah. But after device step, in general, none of them is ordered. Yeah. But this inequality must be true. Otherwise, when we get to the combined step, we will get trouble. Okay? If this inequality does not hold, when we move to the combined step, we need to do some work. We need to do comparisons. We need to do a lot of work. Yeah, so we don't want that. Yeah. Yeah. All right. But the question is, yeah, how do you get that? How do you get that? Yeah. All right. So let's move to the next slide. D.2, partitioning in quicksort. Yeah. So that's device step. Yeah. So we get into the details. Yeah. Partition. Yeah. We need to do a special partition operation. Yeah. So that partitioning process. Yeah. All right. Yeah, so here, divide condition, basically the maximum of a subarray less than or equal to the minimum of b subarray. Yeah, but the question is, it's hard to control, the maximum of a subarray, the minimum of b subarray, how to control. Yeah. So here you have to have some very smart method to make it happen. Yeah. It is smart, but not complicated. It's not very complicated. No. No. But you have to find a very smart, efficient way. Yeah. So let's look at that detail. Yeah. Implement this device step. Yeah. So, all right. So let's imagine we have, this is original subarray. Original. Yeah. Okay. Yeah. When we do it, so we want to gradually achieve our goal. Yeah. Because it's not easy to achieve the goal immediately. Yeah. So we want to do step by step. Yeah. All right. How to split? Yeah. So here we don't know where is the point, the boundary point we can use to split two subarrays. It's unknown. So we need to find a solution for that boundary point. Yeah. All right. Yeah. With that inequality. Yeah. So here there is an uncertainty regarding the sizes of A subarray, B subarray. How many elements in A subarray? How many elements in B subarray? We don't know. Nobody knows that. Uncertain. It is uncertain. How do you address that uncertainty? Yeah, that's a challenging question. Uncertainty. Yeah. So some smart idea is needed to fix that uncertainty. Yeah. All right, so let's see how to fix it. Yeah. All right. How to make it certain, yeah, that boundary point, right? Boundary, element. Yeah. We need some element in the middle, and that special element is used to separate these two subarrays. Yeah. So that element is critical. So we want to study that special element. All right. A special element to separate two subarrays. Yeah. Because that element is so critical, yeah. So we want to give it a special name, yeah. Special concept for that critical element separating two subarrays and satisfying this targeting inequality. Yeah. All right. The key property of that special element. What's the key property of that element? That element must have a very important property. So what's that? That element must be in place. In place, okay? That the location of that element must be the right location after the whole array is ordered. It is in place. Yeah. All right? Then, its left subarray, right subarray are separated by this important critical element, sit somewhere in the middle, but that is in place. It's at the right place. Okay? Yeah. We won't move that element anymore. After it is in place, then we never need to move it out of the place. Okay? Yeah. Yeah. All right. Yeah. So that is its important property. Yeah. All right. But how to make that happen? Yeah. All right. Before we move that, because here I need to connect to our homework question. In our homework question, there is a concept about this in place. So I want to explain a little bit because many students get confused. Yeah. The first question in our new homework assignment, homework assignment 2, question 1, that question about related to this concept in place. But the meaning of in place in that question is different from the meaning of in place here. So I want to explain that difference first. There are two meanings. When we talk about in place, there are two meanings. Okay? I may mention this difference once before, but I couldn't clearly remember in which module, which part. Later probably I go back to my old notes, try to find it. But because I couldn't remember clearly, so I believe many of you couldn't remember. Because when we talk about this in place, there are two different meanings. The first meaning is in place elements. That's the meaning. So you're familiar with. These elements, when they are in the right place after the array is sorted, so we call in place. So that's the first meaning. When you see in place elements, you take that understanding, the first one. But second one, you may not be very familiar. Second one, we use it to describe some special property of algorithms. So usually we use in place algorithms. Okay? In place, this phrase, we use it to describe algorithms, not elements. Okay? So you want to see the difference. So the second one is in place algorithm. And our first homework question, I'm asking you about in place algorithms, not in place elements. Okay? Here, let me give you the meaning of what's the in place algorithm. All right. Regarding the in place algorithm, we look at the storage space. You need to store your data, right? You need to store your data, okay? All right. So the storage space used for input and output, because you always need to store your input output, right? So that storage space used for input output we treat as the normal, okay? Because you have to use the minimum amount of space to store your input output. So that's the normal part, all right? But other than this part, you may need to use more space, more storage space. That the normal part is the minimum amount of space you can use. But above this normal space, you need to use extra storage space. Extra storage space. Sometimes you use a lot. Sometimes you use very little. That part can vary. Okay? Large, small, that part can vary. All right. Our in-place algorithm means the extra storage space other than input-output, okay? Extra part you used is big theta of 1. So very little. So you use big theta of 1. That's the fixed number of constant, bounded by constant. Here, big theta of 1 means, here you use this understanding. Bounded. The number of, because storage in main memory, storage space, we use the memory locations, right? Memory locations. Yeah. Okay. Yeah. There is unit. Yeah. Long integer, or integer, double precision. So you need to use some unit. Okay. Yeah. Bounded by constant number of memory locations. Yeah. So, bounded by a constant number of locations. Okay. Yeah. Okay. Constant number of locations in main memory. Now, could be 2, could be 3, could be 10, but it must be a constant. If an algorithm has this property, so we call it in-place algorithm. For example, here let me use a simple example. For example, selection sort. Selection sort. How do we do selection sort? We find the minimum. Every time we scan the whole array or the current array, yeah, because array, every time when we scan the current array, we find the maximum or minimum. Yeah. Yeah. Could be maximum, could be minimum. Okay. Yeah. When you do selection sort. Yeah. If you use the maximum, yeah, you will need to find maximum, because when we do selection sort, we use a temporary location store current maximum, right? Then you do swap. The temporary location, that's the extra space you used. Okay. Yeah. Then when you do swap, but you only need one extra location for you to store the temporary maximum. Then you do swap. That's all you need, right? So the selection sort has this property. Extra memory storage space you need in big theta of 1. Yeah, that's just one example. Yeah. So use this understanding to answer our first homework question. In that one, I list 4 different algorithms. Yeah. And you need to tell me which one is not in place. Okay? Yeah. 3 of the 4 are in place. Yeah. But there is one of the 4 algorithms, it is not in place. All right? So here, let me clarify the meaning of that in-place algorithm. Otherwise, because based on my experience, many students, before, yeah, so they misunderstood. Yeah. So they use the in-place elements understanding. Okay? So then it does not make sense, right? In-place elements. Yeah. It does not make sense. Yeah. Yeah. All right. Yeah. So let's continue. Yeah. All right. Yeah. Yeah. Let me look at my time I have. Yeah. I need to. Yeah. I still have half an hour. Yeah. So let me try to do as much as I can. Yeah. All right. Determine the boundary of the 2 subarrays. Yeah. Look at the P in the middle. Yeah. Between A subarray and a B subarray, there is a special element. Here I call it the P element. Yeah. Why P? Because we call special name for this element, pivot element. It's so important, so critical. So we call this element the pivot element, P. Yeah. This element, it must be in place. And it is used to separate these 2 subarrays, and these 2 subarrays satisfy these 2 inequalities. The first one, any value in A subarray must be less than or equal to P value, and any value in B subarray must be greater or equal to P value. Okay? Yeah. Because in this way, then we automatically, if we can find that special element P, then our goal, our targeting inequality is automatically satisfied. Yeah. Because we insert a P between these two subarrays. That's the trick. Yeah. So next, the question, how to find that P, right? Yeah. Here, you know, if you can find that P, then we can get that divide step. We complete that divide step if we can find that P. Yeah, based on our analysis so far. Yeah, but we don't know. Yeah, at this point, we do not know how to find that P element. Yeah. Yeah. So next, we want to find that P. Okay. All right. Which element is used as the pivot? Now we need to study around this pivot element. Pivot concept. We study around it. We try to explore its properties. Yeah. Because we have a lot of freedom to choose element to be the pivot, right? Yeah. You have freedom to choose a pivot element. Yeah. All right. Any element has an equal role in the array. Yeah. Given an array, you do not have any information about the values of the elements in the array, right? Yeah. I don't know. Yeah. You cannot predict. You know, yeah. You don't have any information. Yeah. If you do not have any information about the values in the given array, then equal opportunity. Okay? Any element has the equal opportunity to be the pivot element. All right? That means you can select any element as the pivot. Okay? No advantage, no disadvantage. All of them have the same probability to be the pivot element. Equal chance. Yeah. So that's our initial understanding of the pivot. No reason to favor any particular element. Okay? Yeah. Regarding the values of the elements, none of them has better chance than other elements. Equal chance. All of them have equal chance to be the pivot element. Yeah. So that's our initial understanding. Okay. All right. Then next. So when you select a pivot element, you can make a random selection. Okay? Yeah. Yeah. Probability wise, same. Yeah. Probability wise, same. Yeah. Okay? Yeah. All right. But position wise, then it's different. Position wise, yeah. Because given an array, there are different positions. There are different positions. Some elements in the middle, some elements near the end. The position situation quite different. Now, we want to look at the which position is more friendly for the pivot element? More friendly for, yeah, because if you consider the position of the elements, then some of the elements are better than other elements. Some of them have better positions. Better means more convenient. Some elements are more convenient. Convenient for what? Convenient for algorithm implementation than other elements. No, because the position, location. Yeah. Think about an array has this line structure. The position of the elements in array, then definitely, if you look at the positions, that's quite different, right? Yeah. Think about if you have a line of apartments, okay? Yeah, the locations definitely, they're quite different, right? Yeah. Yeah. The apartments at the two ends, definitely different from apartments in the middle, right? When you rent one of the apartments. Think about that. Here also, in our array, if you look at the locations, definitely all, these elements, their locations play different roles in algorithm implementation. Yeah. Yeah. All right. Well, then we need to study the locations. Which location is most friendly for the pivot element? We need to pick the best location for the pivot element. Yeah. All right. Yeah. So look at this diagram. Think about if we pick one arbitrary location in the middle in this array, we consider how about we select this location for our pivot element. Pivot. Yeah. Because you can do random selection, right? Yeah. Value-wise, you can select randomly, but position-wise, then you want to make your best choice. All right. Think about if you select this location in the middle of the array to store your pivot, what would happen? What would happen? Yeah. First, you do not know this element is in place or not, right? In general, it's not in place, right? How can you select element, in arbitrary location somewhere in the middle and it will be in place? No. Most likely, it's not in place. So that's the first difficult problem. Not in place. If it's not in place, then you need to move around, right? Yeah. You need to move this and move around. Yeah. At the end, it must be in place. Okay? Initially, it's not in place. But at the end, it's in place. But you need to move around. Right? Yeah. Yeah. But when you move around, also think about, for other elements, you also need to move around, right? For other elements, you also need to move. Otherwise, you won't get your destination inequalities. You won't get these two inequalities. Okay? You have to move elements around, all right? Yeah. But when you move elements around, it's not very convenient, because this pivot element sit in the middle, just like a roadblock, right? Yeah. It's like a roadblock. When you move elements around, then you need to, when you hit this roadblock, you need to do more work, right? Yeah. It's hard. It's hard. Yeah. When you have a roadblock in the middle and you need to move elements around, too much work. That means the position like this is not friendly to hold our pivot element. Yeah. Okay? Yeah. We don't want to have a roadblock. Okay? We want to remove the roadblock when we move elements around. No roadblock. Okay? If no roadblock, then very easy to move elements around. Right? We never hit roadblock. Right? Yeah. So what special positions, if you choose to store your pivot element, then you won't have roadblock when you move elements around. Yeah. Yeah. So roadblock. So we drop it. Yeah. We don't select it. Yeah. Then only two special locations at two ends. Left end, the star location, right end. If you store your pivot element at one of the two end locations, then there won't be the roadblock, right? They won't block any element adjustment moving around. They won't block anything, right? You leave them alone, okay? Yeah. We just pick one of the two special locations at two ends. So we won't have the roadblock. So these two locations are the most friendly locations to store our pivot element. So this analysis is important. Yeah. We need to use these two special locations. Yeah. All right. So then, yeah. All right. Now, to describe the algorithm, so I use the rightmost end location to store the pivot P element. Yeah. All right. Then let's do the remaining part of the partition step. Partition. We need to get A subarray and a B subarray. We have P, so here, location, to hold that P temporarily, okay? Yeah, so this location, convenient location, that won't be the end location, okay? It's the temporary location, not the destination location. Yeah. So we will drop this P at its destination location at the end. When we find the A subarray and the B subarray, then we will find the right location for this P element. All right. Yeah, so then A subarray, B subarray, like that, with the condition any element, its value in A subarray less than or equal to P, and P also less than or equal to the value of any element in B subarray. Yeah. All right. D.3, implementation in partitioning. Yeah. Now, how to get A subarray, how to get B subarray. Yeah. So we will find the details in D.3. Yeah. All right. Straightforward implementation. Regarding implementation, we separate into two parts. First, we want to have an easy implementation, straightforward, easy implementation. Then we improve it to get a better implementation. All right, let's look at the straightforward implementation. Use two auxiliary arrays. For the straightforward, we just want to get it to work. It may not be the best way. Just get it done. Then we'll improve it. Yeah. The first try, usually not the best way. Yeah. The first try. Yeah. Just make some progress. Not the best way. All right, so let's do the first try. After we, because value-wise, all the elements have equal chance. So let's just pick the last one as the pivot. All right? Now, for convenience, pick the last element as the pivot. So in our textbook, it may pick the first one. But idea is the same. Okay. All right. Now we scan the array from left to right. Scan the whole array one by one from left to right. Every time when we get a current array, we compare it with the P. We compare its value with P. Two cases. First, it is less than or equal to P. Second, it is greater than P. Only these two cases. Then, based on which of the two cases we can put the current element in one of the two subarrays, A subarray and a B subarray. Okay, all right. So let two auxiliary subarray, right? So the first auxiliary subarray to store the destination A subarray elements. Second, for B subarray elements. But how to get A, how to get a B? You pick from original array, each element from original array. If it is less than or equal to P, you drop it into A auxiliary subarray. If it's greater than P, its value greater than P value, you drop it to B auxiliary subarray. So easy, right? After you complete the scanning, all the elements except the P, you get an A subarray satisfying the first inequality, and you also get a B subarray satisfying the second inequality. Then, after that, you copy these two auxiliary, the values, the elements, their values in these two auxiliary subarray, you copy them back to the original array, then you get what you need, right? You get a partition. You get that partition. Okay? But the question, is the solution acceptable? Is there any improvement you can do for this solution? Yes, because when you use two auxiliary subarrays, you use too much extra space. Auxiliary subarrays, that's the extra space you use. Extra space. We want to save as much as possible the extra space. So here, the question is, can we avoid using these two auxiliary arrays? If we can avoid, then we save a lot of extra space. So our next step, improvement, we want to eliminate these two auxiliary subarrays, auxiliary arrays. That means we can only use the space in our original array. We don't want to use two auxiliary subarrays. All right? So that step also important. All right? But that step a little challenging. How to avoid, how to implement the partition step without auxiliary arrays. Yeah. Yeah. So here we want to control extra space used. Extra space used. All right? Yeah. Minimum. We want to make the extra space used. Yeah, you may need to use some extra space, but we want to make the usage of extra space to the minimum. Okay? Yeah. All right. Let's look at the last step. Now we need to manage the locations in the original array. Manage their locations efficiently. Because those storage space very precious. You don't want to waste your storage space. Yeah. All right. Yeah. So we want to find a, nice way to manage those locations. Yeah. All right. S region. Yes. First, we define a special region called S region because the elements in this region should be smaller or equal to the P. S here means smaller. Okay. Smaller or equal to that P. Yeah. Then L region larger. Yeah. So the elements in this region, L region, its value will be larger than the P value. Yeah. Okay? Yeah. But we need a special region containing the elements unprocessed. U means unprocessed. Yeah. Before we know if the element in this region is smaller or larger than P, unknown. Yeah. So we leave them in this U region. Okay. The reason we use these three regions, so we want to do the bookkeeping. Okay. Yeah, bookkeeping, manage, organize our data in this way. Yeah. All right. Yeah. So let me use the final 5 minutes to complete describing this idea. All right. In a subarray, all the elements in subarray should be in this S region, and all elements in B subarray should be in this L region. Yeah. But at the beginning, when we start scanning the array, initially these two regions are empty. Yeah. No elements in each of the two regions. Empty. Yeah. But every time when we do comparison, we grow. We grow these two regions. Yeah. When we add elements in one of the two regions, we grow these two regions. Yeah. The unprocessed, initially, it's the whole array except P. Yeah. All right? But at the end, after we finish the scanning, the whole array, then this U region becomes empty. Yeah. So we only have S region and L region. Then you complete the partition. You complete it. Complete the partitioning step. Okay? Yeah. Yeah. So that's simple. So the idea, not that complicated. Not that complicated. Okay? Yeah. All right. But after you see this idea, next, then we need to, because at this point my description is very abstract, right? Yeah. You may not see it clearly. Yeah. Although you see some, vague description, right? Vague description. Yeah. Yeah. But not very concrete. Yeah. Still too abstract. Yeah. So you want to see something concrete. Yeah. So we need some example for partitioning. Okay? D.4. Yeah. Let me see if I have time to run. Yeah, I may still have 3 or 4 minutes. Yeah, so let me run this example to let you see clearly how to do a typical partition step. Yeah. So let's start with a concrete example. Yeah. So an array with these numbers. Yeah. So we want to do a one partition step. Yeah. The last element we use it as the pivot. Okay, then let's initially all the elements except the pivot all in the U region in white color. We use different colors to mark elements in different regions. So the white color for the U region elements. Yeah. Extra space we use to do the swap operation. Okay, one extra space, swap operation. All right. Then let me run comparison. Let me see. Yeah. Time control. Oh, I don't have 2 minutes only. Start. Let me just do a few steps. Okay. Yeah. If I couldn't complete the next time, then I do it again. All right. Initially, S region empty, L region also empty. First comparison. Compare 2 and 4. 2 is less than 4, so we should drop it into the S region. Yeah. Okay. Or we should mark it. So we should, mark it in S region yellow color. Okay. Second comparison. Compare 8 and pivot 4. 8 is greater than 4, so we should put it in the L region. So we use green color to mark this element. All right. Third one. Compare 7 and 4. 7 greater than 4. So it should be in green color. All right? Yeah. See? Yeah. So far, so good. Yeah. Comparison number 4. Compare 1 and 4. 1 is less than 4. So it should be in S region. And we mark it yellow color. But this time, 2 elements in yellow color, they are separated by the green region. It's not good. We want all the elements in yellow color in the same region, back to back, same region, occupying consecutive locations. So here we need to do one swap operation to get that. Yeah. How do the swap operation? Yeah. Swap element 8 and element 1. After that swap operation, you use that swap space to do swap operation. After that swap, then the 2 elements in yellow color, they are in the, occupy consecutive locations. Yeah. And also, elements in green color occupy consecutive locations. And so on. We can keep doing like that. All right. All right. I run out of time. So let me stop right here.